Okay, so guys, let me share my screen just to show you guys what's in Schoology. So remember last time we started thermodynamics, which is basically talking about heat and energy and heat change. So we introduced that. We talked about conduction, convection, radiation, and things like that. So basically, we focus on some important things conceptually. Today, we're going to get more mathematical, in that we're going to be dealing with actual calculations involved in heat energy. So that's the goal for today. So today is February the 3rd. It is a Wednesday. Okay. And so here's what we're going to do. I'm going to go over a little bit of this PowerPoint. Um, if I were you, the equation that's in this PowerPoint, the one equation I'm going to give you guys today, I would write that down because this is the equation that we're going to use for our assignment. So we're going to go over the PowerPoint. Then I'm going to do a few example problems with you guys involving heat calculations. And then as soon as we get done with the class, I'm going to make this assignment available to you all for you all to complete on your own. So this is what you're doing on your own, heat calculations. It is a multiple choice assignment. And again, all of this is in the folder for today. Okay. Now, okay, before I begin that PowerPoint, I want to be sure to define a term here that everyone has heard before, but may not have necessarily thought about what it means. And that term is temperature. So everybody in here is familiar with temperature, right? You're familiar with something being hot or cold. You guys also know how to measure temperature. You measure temperature with a thermometer. This is something you guys are all familiar with. But what exactly do we mean when we say temperature in terms of how scientists define it? Well, guys, whenever scientists determine a measurement of temperature, what they are referring to the average kinetic energy of the molecules that make up the substance. So, as I'm going to show you guys here in this video clip.
As the temperature inside the jar decreases, the water vapor molecules move more slowly. And as the temperature increases, the water vapor molecules move more quickly.
Okay, so everybody see that, guys? So that's what we mean by when we say temperature. We're talking about the kinetic energy of the molecules that make up a substance. So imagine these were water vapor molecules inside this jar. Y'all clearly saw that as the temperature went down, those water vapor molecules, as they're moving randomly, they begin to slow down. But as we increase the temperature, those water vapor molecules begin moving faster and faster, and they begin to speed up as the temperature went up. So that's what we mean by when we say temperature. That's what temperature is, guys. Anytime something is hot, its molecules are moving really fast. Anytime something is cold, its molecules are moving really slowly. So that's what we mean by when we say temperature. We're just talking about the average kinetic energy of the molecule that makes up the substance. Devin, there goes the attendance form for you. So keep that in mind. Okay. Okay. So looking at this PowerPoint here. Like I said, we are in our thermodynamics units. We're going to spend about a few days on this unit. Thermo means heat, dynamic means change. So, it should be obvious that what we're studying, in this unit, we're just dealing with heat and changes of heat involved in different systems. So, just something to keep in mind. Okay, so we've already measured what temperature is. Temperature is a measurement of how hot or cold something is. To be specific, temperature measures the average kinetic energy of the molecules that make up a substance. Okay. Temperature can be measured in units like Fahrenheit or Celsius. We can also measure temperature in Kelvin, which we're going to talk more about next week. Um, okay, so we're going to focus more on Fahrenheit and Celsius next week. What I want to talk about today, I want to talk about the specific heat equation. Okay, um, this equation right here, I would write this equation down because this is the equation that we're going to use today. Um, um, Q times M times C times delta T. So if I were you all guys, I would write this equation down. In just a moment, we're going to explain what each of these terms mean. So Q is equal to M times C times delta T. Okay. So write this equation down because this is what this equation is what we're going to use today. Okay. So Q stands for the heat energy added to a substance. M stands for the mass of the substance. C is what is known as the specific heat capacity of the substance, and this is just a constant for different substances. And delta T stands for the change in temperature of the substance. Okay. Before we use this equation, real briefly, let me explain to you guys what this equation means and what this equation tells us. Imagine that I had a block of water, or a block of ice, I should say. So imagine that I had a block of ice. So if I had a block of ice, and imagine that I put this block of ice in the microwave, just kind of imagine it for a second. As I put this block of ice in the microwave, obviously I am giving the ice energy, right? So energy from the microwave is going into that ice, okay? So the amount of heat energy that we put into that ice, that is what is known as Q, right? So the microwave is giving the ice heat energy, okay? Everyone in here knows that as this ice receives energy, eventually it's going to melt, right? Because it's being heated up. So in other words, its temperature is going to rise. So in other words, its temperature is going to go up. Its temperature is going to increase. Okay. So, guys, that's where this equation right here comes in. This equation right here mathematically tells me if I know how much energy I give this substance or how much energy I give this block of ice, then I can mathematically predict exactly how much its temperature will increase. That's what this equation tells me. Again, assuming I know the specific heat capacity of the ice, which is going to be given to you guys in many of the problems. Okay, so that's what this equation means. Okay. All right, everybody got that? And guys, the same thing is true of a substance if I take energy out of it. So, for example, like imagine I take something, um, and I put it in the refrigerator. If I take something and put it in the refrigerator, obviously it's going to cool down, right? Because the refrigerator is going to take energy out of the substance. And so as it takes energy out of the substance is going to decrease. So if I know how much energy I take out of a substance, then I know how much the substance is going to go down. Okay. So write down this equation because this is what we're going to be using. Okay. And I will write down what each of these terms means. Again, Q just stands for the quantity of heat energy added to our substance. Okay, that's what Q stands for. Yes, sir. Excuse me, you have your expo cleaner. Guys, give me just a second.
You like mine.
I don't have a bunch of it.
That's what I don't worry about it. I'll try something else.
See if you can spray a little bit out. I have something, but I'm gonna have to pour it in there. See what you squeeze out of this.
Oh, that'll be fine. Thanks.
No problem.
Sorry to interrupt.
No, you're good. So, guys, Q stands for the quantity of heat energy added or taken away from your substance. M stands for your mass of your substance. And some of the problems, mass is going to be measured in grams. Some of the problems, mass is going to be measured in kilograms. Okay. So again, if I were you guys, I would write this down because this is the most important equation we're going to be using today. Okay. C stands for the specific heat capacity of the substance. And guys, C is just a constant. Different substances have different specific heat values. For example, water, because it's different from aluminum, is going to have a different specific heat capacity compared to aluminum. This constant right here is just a measurement of how hard it is to change the temperature of that substance. That's all. It's just a constant for different substances. So obviously, aluminum, iron, zinc, since those are three different substances, they have different specific heat capacity values. And that will be given to you in some of the problems that you're going to be solving. So again, I will write this stuff down. And lastly, T stands for temperature change. In other words, change in temperature. Everybody got that? One more thing that I want to say here before we move on from this PowerPoint. Look at Q, guys. Okay, if you have a substance and you add energy to that substance, Q is positive. So if energy is added, Q is, well, let me write that down somewhere. Let me write it here. So in this case right here, if we're adding energy, Q is positive. Okay. So if energy is added to a substance, if energy is added to a substance, Q is positive. If energy is taken out of a substance, Q is negative. So everybody got that? If energy is added, Q is positive. If energy is taken out, Q is negative. Just something to keep in mind for that equation. Okay. So hopefully everybody got, if energy is added to a substance, Q is positive. If energy is taken out of a substance, Q is negative. And the last thing that I want to say here, okay. If you guys see right here, this delta T, remember what delta T means. Delta T, if it means change in temperature, it is always the final temperature of a substance minus its initial temperature. Okay. So remember that. That's what delta T means. So delta T means change in temperature. It's the final temperature of a substance minus its initial temperature. Okay. Okay, hopefully everybody got that and we're ready to work out these sample problems using our equation. Okay. Let us do some practice problems together, just so you guys will have enough information to be able to work these things out on your own. now. Okay, let me go ahead and share my screen. So we're going to do about 6 of these problems together, just so you guys will have enough information to work these problems out on your own. Okay, now look at number 1 here. So number one says gold has a specific heat of 0.129 joules per degree Celsius. How many joules of heat energy are required to raise the temperature of 15 grams of gold from 22 degrees Celsius to 85 degrees Celsius? Okay, so let's do this. So number one, remember what our equation says. The amount of heat energy, Q, is equal to the mass of the substance times the specific heat capacity of the substance times the change in temperature of the substance. Remember what change in temperature is. Change in temperature is the final temperature minus the initial temperature. Okay. So guys, that's the equation that we're going to use for number 1. Okay. So let's fill everything in. Okay. It tells us we're solving for heat energy. So in other words, we're solving for Q. Okay. So the mass of the gold is 15 grams. Okay. So we're going to plug in 15 for mass. We're also told what the specific heat capacity of gold is 0.129 joules. Again, that's given in the problem. So basically 0.129 joules. All of that gets multiplied by the change in temperature. What was the final temperature? The final temperature of the gold was 85 degrees Celsius. And the initial temperature was 22. Okay. Guys, so the rest is just putting everything in your calculator. What is 85 minus 22? That is equal to 63. So just do the math. Q is equal to 15 times 0.129 times 63. Okay. And then when you put that in your calculator, you get Q is equal to 121.9 joules. And guys, we use the units joules for heat energy because remember, that's what we use for energy is joules. Okay. So guys, that is number 1. Okay. Everybody got that? Any questions? Any questions? Everybody got that written down? That's writing. I know sometimes some of you guys like to write these things down. So whenever you're doing this on your own, let us look at number 2. Oh, number 2. This is going to be an interesting one. This is going to require that we do a lot of algebra here. As you guys are going to see why. Just a moment. Okay. So number 2 says a 40-gram sample of water at 25 degrees Celsius absorbs 500 joules of energy. What is the final temperature of the water? The specific heat of water is 4.18. Okay. So notice what we're solving for here. We're not solving for Q here. We're actually solving for final temperature. So let me write down my equation. Okay. So remember, our equation is Q, the heat energy going into a substance, is equal to the mass of the substance times the specific heat of the substance times the change in temperature. Where it's understood, change in temperature is the final temperature minus the initial temperature. Okay. So guys, in this problem right here, in number 2, what we're trying to solve for, we're trying to solve for this. We're trying to solve for the final temperature. And this is going to involve some algebra. So let's plug everything in. We're told that the water absorbs 500 joules of energy. So in other words, we're given Q, and Q is positive, guys. Q is positive here because it absorbed the energy. In some cases, if energy is lost, Q is negative, but in this case, Q is positive. So 500 joules of heat energy was absorbed by the water. The mass of the water is 40 grams. So you guys can see that. So 40 grams. We are also we're also given the specific heat of the water, which is 4.18. 4.18. All of that gets multiplied by final temperature, which is what we're looking for, minus the initial temperature. What is the initial temperature of the water? We're given that. It says the sample of water was at 25 degrees Celsius. So that's the initial temperature of the water. It was at 25 degrees Celsius. Okay. So guys, we need to be able to solve this equation for final temperature. We need to be able to get final temperature by itself. This is going to take some significant algebraic steps. So, which is what I want to do now. So I want to go through the algebra with you guys. So here's how we're going to do this. In order to get final temperature by itself, the first thing we need to do, let's multiply 40 times 4.18, and let's see what that is. So 40 times 4.18, that gives me 167.2. So 500 is equal to 167.2. And that gets multiplied by the final temperature minus the initial temperature. Okay. We're not done, because remember, we have to get final temperature by itself. Okay. But guys, in order to do that, I need to get rid of this parentheses first. In order to get rid of the parentheses, this 167.2, I'm going to take that and I'm going to distribute that first. I'm going to take it and I'm going to distribute it. So that's just algebra. When I distribute that, this is what I get. I get 167.2 times my final temperature. And then I have to do 167.2 times 25. That gives me 4,180. Okay. Y'all follow me so far? Okay. Let's keep going. Remember, our goal is to get the final temperature by itself. So let's keep doing the algebra. Okay. Y'all see this negative 4,180? I need to move that to the other side of the equal sign. In order to do that, I have to do the opposite of subtraction, which is to add. When I do that, that goes away. Whatever to the one side, I have to do to the other. So 500 plus 4,180, that's 4,680, is equal to 167.2 times the final temperature. Okay. Last step, guys. How do we solve for final temperature? How do we get final temperature by itself? It's easy. We divide by 167.2. So that goes away. Whatever to one side, we have to do to the other. So if I put this in my calculator, turns out I get 27.99 degrees Celsius for my final temperature. That is number 2. And guys, I promise this is going to be the most tedious problem on here. All the other problems are not this tedious. But that's how you do number 2. Okay, that's how you solve for the final temperature in degrees Celsius. Any questions? Okay, let's keep going. Let's look at number 3. Number 3 says copper has a specific heat of 0.385 joules per gram per degree Celsius. A piece of copper absorbs 5,000 joules of energy and undergoes a temperature change from 100 to 200 degrees Celsius. What is the mass of the piece of copper? Okay, so in this equation right here, we're actually solving for mass. So let's do that now. So let's write out our equation. Q is equal to mass times C times change in temperature, where it's understood that the change in temperature is equal to final temperature minus the initial temperature. Okay. And now Q stands for heat energy. Okay. So our goal here is to solve this equation for mass. So we're on number 3 and we're solving for mass. Okay, let's plug in what we have. Okay. We're told that the copper absorbs 5,000 joules of energy. Okay, so that means we are given Q. So 5,000 joules of heat energy is Q. Okay. We don't know what the mass is. That's what we're trying to find. Okay. But we do know what C is. C is the specific heat of copper, which is 0.385. So 0.385 is the specific heat of copper. All of that gets multiplied by the final temperature of the copper. Notice the final temperature of copper was 300. I'm sorry, not 300, 200. The final temperature of the copper was 200. And the initial temperature of the copper was 100. Okay. All right, so remember, our goal is to get mass by itself. Okay. So I'm just going to simplify this further. So 5,000 is equal to mass times 0.385. Okay. And 200 minus 100, y'all know what that is. That's just 100, right? So the change in temperature is 100 degrees. Okay. All right, so guys, let's keep going. Let's do the algebra. Okay. So if I multiply these two numbers by each other, what I get 38.5. So 5,000 equal to mass times 38.5. And that's what I get when I multiply 0.385 times 100. Now guys, the last step here is to solve this equation for mass. Okay. And you guys know how to solve that equation for mass. You guys know how to get mass by itself. So this is where the algebra comes in. We have to divide this side of the equation by 38.5. That goes away. Whatever you do one side, I have to do to the other. So if I put 5,000 divided by 38.5 in my calculator, what I get a mass that is 129.87 grams. Okay. So that right there, that is number 3. Any questions? So the mass of the piece of the copper is 129.87 grams. Okay. Let us keep going. Let us look at number 4. Hello? Okay. All right. All right. Bye. Number 4 says an unknown substance with a mass of 100 grams absorbs 1,000 joules while undergoing a temperature increase of 15 degrees Celsius. What is the specific heat of the substance? Okay. So this case right here, we're actually solving for specific heat. Okay. So we're in other words, we're solving for C. So let's write our equation down. Q is equal to mass times C. And in this problem, we're actually given the change in temperature. We were actually told that the substance went up. That means it's temperature increase. So we're actually given the change in temperature in this particular problem here. We want to find specific heat. So let's plug everything in. So so it says it absorbs 1,000 joules of energy. So it absorbs 1,000 joules of energy. So 1,000 is Q. And so, and we know this is energy because our unit is in joules, which is the unit for energy. The mass is 100 grams. We're trying to find C. We don't know what that is. But we do know the change in temperature, or the temperature change. Remember that it increased by 15 degrees Celsius, so the temperature change was just 15. Okay. The last step here is to solve this equation for C. 100 times 15 is obviously 1,500. So 1,500 times C. And you guys know how to solve that equation for C. In order to solve this equation for C, we're going to have to divide by 1,500. So we're going to divide this by 1,500. That goes away. Whatever we do one side of the equation, we're going to have to do to the other. Okay, so guys, if I put 1,000 divided by 1,500 in my calculator, what I get C is 0.67. And of course, you know, the units for C is this. But most important thing is when we solve for C, we get 0.67. So in the case of number 4, the specific heat of this unknown substance is 0.67. Okay. Okay. Let's just do one more. Let's just do one more. I think if I do one more, you guys get the point. Look at number 5. Number 5 says graphite has a specific heat of 0.709. If a 25-gram piece of graphite is cooled from 35 degrees Celsius to 18 degrees Celsius, how much energy was lost by the graphite? Okay, I want you guys to notice something. Notice it said the graphite was cooled. In other words, energy was lost. So remember, when we solve for Q here, our Q value better be negative. Because remember what I said, if you lose energy, Q is negative. If you gain energy, Q is positive. Okay, so in number 5, just so we're clear, in number 5, Q better be negative because energy was lost. Okay, so um, let's look at that right now. So let us write our equation. Q is equal to mass times C times delta T, change of temperature where it's understood. Delta T is the change of temperature. In other words, it's the final temperature minus the initial temperature. Okay. That's what delta T means. Okay. And guys, what we're solving for, we're solving this equation for Q because it says how much energy was lost. So we're looking for heat energy. That's what we're solving for. Okay. We're looking for how much energy was lost. So the mass of the graphite is 25 grams. So let's plug that in for that. The mass of the graphite was 25 grams times C. We're given the specific heat of graphite is 0.709. So plug in 0.709. Okay. All of that gets multiplied by the final temperature minus the initial temperature. Notice, guys, the graphite was cool. So if the graphite was cool, the final temperature is lower than the initial temperature because it lost energy. It cooled down. So that means the final temperature is 18. And the initial temperature here is 35. Okay. So that's my equation set up. And the goal is to solve this equation for Q. First of all, I want to do 0.09. I'm sorry, not 0.09 times 25. What I want to do, I want to do 18 minus 35 first. Okay. If I do 18 minus 35, what is that? 18 minus 35, notice that gives me a negative 17. Okay. It gives me a negative 17. Okay. Now, in order to solve for Q, guys, let's put this in your calculator. 25 times 0.709 times negative 17. Okay. When I do that, when I put all that in my calculator, turns out I get negative 301. Make sure this decimal is right. Negative 301.3 joules. So, and hopefully, guys, it makes sense to you guys why Q is negative. Q is negative because we lost energy. We lost energy. Since the graphite lost energy, Q has to be negative. Okay, and that's exactly what we find here. Okay. I think we've done enough of these example problems for you guys who should be pretty good on your assignment. Okay. Are there any questions for me? Any questions? Any questions about this equation? Any questions about the 5 problems that we just done? By the way, on number 6, guys, again, if y'all want to work out number 6 by yourselves, just to be sure you get the right answer. In this case, if you work out number 6, the answer here is 2.44 is equal to C. But again, that's something if you guys want to practice on your own before you guys do the assignment, that's up to you. On number 6, that's the answer to number 6. That's something you guys want to do on your own. But I think we worked out enough to where you guys are good. Any questions for me? I'm going to put the attendance form in the chat box. For those of you guys who did not get to fill it out. Okay. So just put the attendance form in the chat box. And I'm going to stop it